see how this works. What do you guys see now? Do you see the thing with multiple screens on it, or do you just see the one slide?
We don't. I can't speak for anyone else, but I don't see anything. I don't see a shared screen yet.
Okay. Well, that may not be how I do it here. So let's try this again. Begin screen sharing. Let's see. Share screen. Entire screen. Try this one. Let's see if this works. Can you see anything now?
No, we don't.
Dang.
Alternatively, if if you want to send, if your PowerPoint is small enough, if you want to email it to me, I can put it up on my computer and share the screen and run the slides for you.
All right, let me do that. It's probably something to do with the stupid firewall here. Okay, so let me see here. This is Andrew, right? Or what email address should I send it to?
The andrew.k.bumbach@afis.usda.gov.
Okay. Yeah, it's not too large of a file, so it should go there relatively quickly. Okay, it just went off. Yeah, it's probably some crazy permissions thing that our PC people made us have to do.
I totally understand. We have to jump through some hoops ourselves. So.
Hi, folks. This is Lori.
Hey, Lori, how are you?
Hi. Paul, it's so good that you're joining us. Thank you.
Yeah, we're trying to overcome the technology.
Well, let me know when we're ready to start it off.
Hopefully fairly soon here.
I BCC'd myself on it, and it just got back to me, so you should hopefully get it soon.
Okay. All right, there we go. All right. Does everybody see? Oh, actually, hold on a sec. All right. Does everybody see my screen now?
I do not.
I do.
Don't?
I do see it.
Okay. You see it. Paul, you don't see it, though.
I do not.
Interesting.
What do you see, Paul?
Well, I'm trying to reconnect, see if that works.
Sounds good.
Okay, continue without camera. Okay, I see. Yeah, I see now PowerPoint with all the stuff on the side, and yeah, now I see the thing with multiple windows on it.
Okay. So do you see just the single slide now, your title slide?
Yes.
Okay. All right. Good deal. All right. All yours, Paul, and just tell me when you want me to advance.
Okay. Well, I appreciate the opportunity to talk to everybody about this. I was asked to talk about issues related to emissions of pathogens from mobile and transportable incineration technologies. So you can go on the next slide. And so I'll talk a little bit about what we know about pathogens and incineration in general. I'll talk about some of the testing that we've done at our research facilities looking at destruction of pathogens from incinerators. Talk about the various transportable or mobile incineration technologies that we have a little bit of experience with, and I'm sure there's a lot of other possibilities that you guys have probably had much more experience than me out in the field with. But we'll talk about the transportable gasifier and air curtain burners. And the issues that we see from these two sources are probably the same types of issues you're going to see from pretty much any other mobile thermal treatment type of technology. Next slide. Now there's a hierarchy of the hardiness of biological agents, and they use this this scale mostly when they talk about disinfection, you know, and how hard it is to use chemicals to kill the agents. But the same hierarchy applies to thermal treatment with autoclaves or combustion. And generally, the ones at the top of the pyramid are the ones that are the most difficult to destroy, like prions, bacterial spores, and then as you get down to the bottom of it, you end up with like the viruses, like foot and mouth disease, and they're fairly easy to destroy thermally. As far as data goes, there's going to be a lot of data on spores and a lot less data on the other ones, just because it's difficult to analyze these organisms in environmental samples like you see from a combustion source. And so because of the difficulty and expense in doing the tests are done a lot with spores, assuming that you'll be able to kill anything else if you can kill the spores. This pyramid, though, is there's a huge caveat with this, and that is that the substrate that the organisms are bound up in has a really profound impact on the ability to thermally treat them. If they're bound in a material that, for example, has a lot of water, anybody who took their high school chemistry, when you watch the water boil, it gets up to 100 degrees C and it stays there. And pretty much an animal carcass is going to be the same thing. If you have a large mass of animal, no matter how much heat you throw at it, it's not going to significantly increase in temperature until the water's driven off. And then you'll be able to get to the higher temperatures. We've done a lot of work on building materials, and ceiling tiles, for example, are really pernicious because they could probably tile the space shuttle with ceiling tiles. They're extremely refractory, and they hold a lot of water. Next slide. So incineration essentially is high temperature combustion. Most of the fixed site incinerators and some of the transportable ones that you see will have a primary chamber and a secondary chamber. Usually the primary chamber is where the materials are fed into, and they may not operate at as high a temperature as the secondary chambers, but the primary chambers will effectively kill a lot of the microorganisms. It'll release combustion products and particulate matter into the gas phase, and it generally generates the residual bottom ash that gets dumped out and recovered and brought to a landfill or some other type of disposal method. Then there's a secondary chamber, which is usually like a large box, and the gases pass through that. Sometimes you have burners in there to apply additional heat, and they typically have to stay in the secondary chamber at a certain temperature, like 1,000 degrees C or 1,800 Fahrenheit, depending on how you look at it, for a couple seconds. And coming out of the secondary chamber, you'll have some fly ash. You have acid gases. Sometimes you'll have organic material in the gas phase. Sometimes you'll have organic material bound onto the fly ash. Like dioxins in particular are typically formed downstream of the secondary combustion chamber. So sometimes incinerators will have air pollution control devices to catch the particulate matter and acid gases and to prevent the formation of pollutants like dioxins and furans. It doesn't always happen that way with some of the transportable facilities, though. They may have less restrictive requirements because it's an emergency response that they're being used for, or the technology itself may not require complex air pollution control devices. But most incinerators have some sort of air pollution control device and a primary and a secondary chamber. Next slide. I still just see the one slide. Oh, there we go. Oh, somebody's PowerPoint crashed. I hate it when that happens.
Well, right. Sorry, I was muted. Are we on the right slide now?
One before this, I think.
Okay.
Yeah, I think one more before that, maybe.
Okay.
No, you're right. It's the one after this. Sorry about that.
Okay.
Well, there is not a lot of full-scale data out there on pathogens from incinerator systems systems, because in order to measure them coming out the back end and have it be so you're not just driven by your detection limits, you have to put a lot of your surrogate organism in the front end. And back in the 90s, when the EPA was trying to figure out how to regulate medical waste incinerators, they did a series of tests on the field units that were out there, and they doped the waste with large quantities of Geobacillus stereothermophilus, which is a spore-forming bacteria that is commonly used for performance assessment of autoclaves. And they wanted to look at whether the spores got out the stack or whether the spores ended up in the ash. And so they would put like 10 to the 9th spores per, I think, per kilogram. They put a huge quantity of spores in there. They ended up, after doing these tests, they decided that that was not the best way to do performance testing on medical waste incinerators. So they kind of abandoned that, and we resurrected the data that they took and looked at it to see what it said. We've also done a number of tests at our pilot scale facilities here in Research Triangle Park, where we were looking at embedding spores into bundles of different types of building materials and looking at time and temperature for achieving the destruction of the spores. We also wanted to look at the impact of some of the disinfectants that might be used and end up in the waste that you would process through the incinerators. And since bleach is a commonly used disinfectant, we wanted to see what impact the bleach would have on the combustor emissions. Next slide. And what we found on the medical waste data, yes, I'm still seeing the one slide. There we go. We found that the test data from the medical waste incinerators is, in most cases, they achieve 6 log reduction for most of the facilities. But there was a handful of facilities, like 2 or 3 of them, where they achieved less than 3 log reduction. And when we looked at a statistical analysis of the operating conditions, we found that the primary chamber temperature and the secondary chamber residence time were the ones that were most statistically significant in determining the level of destruction that we saw. So we thought that was kind of interesting. If you look at the graph that's up in the upper right corner of this slide, what we found from our spore destruction tests is that no matter how long you left the material in the incinerator, if you could make sure that the coldest part of the slug of material that's in there got to 350 degrees C, then we didn't see any spore survival. So we thought that was kind of interesting in that the incinerator was operating at 1,000 C for some of the test conditions, and we were pulling live spores out after 35 minutes that were embedded in wetted ceiling material, ceiling tile. Because, again, it took 20 or 30 minutes for the water to boil off before you really started seeing the material come up to temperature. We also found that we were burning carpet that we had dunked in diluted bleach, and we found that it indeed could potentially lead to increased dioxin emissions. So if you're sending your materials off to a fixed facility and they're running on the ragged edge of their dioxin compliance, they may want to think twice about accepting large quantities of material that has bleach in it. So, because it could potentially impact their emissions that they're permitted for. Next slide. So overall, what we found as implications of some of these tests is that if you can get the waste mass up to 350 C, you're going to kill all the microorganisms. For those that get into the gas phase, making sure that you achieve your primary combustor primary chamber temperature and the residence time in the secondary chamber, that'll assure destruction. The ash is not likely to have any microorganisms, but there may be secondary requirements for disposal of the ash, like test for toxic metals or things like that. When you're dealing with viral threat agents like foot and mouth disease, it's killed off at about 50 degrees C. And so the ash leaving the incinerator is almost always well above that. Usually they have to drop it into a water bath in order to drop the temperature down so that you don't damage your ash moving equipment that you use to put it into whatever roll-offs that you're going to use to send it off for disposal. And bleach is important. If you're going to use it as a disinfectant, it could potentially impact your emissions from your incineration processes. Next slide. So now talk a little bit about some of these transportable technologies. Lori and us have done some work over the years looking at gasification as a transportable technology. For those who aren't familiar, gasification is a starved air combustion type of process where you have your primary chamber and you don't put enough air in to completely burn out the materials. So the gases that leave the primary chamber have enough heating value that they may potentially be able to self-sustain the combustion in the secondary chamber without having to add much fuel in order to maintain your temperatures. So because you aren't dumping a lot of air into your primary chamber, there's lower flue gas flow rates, and you might be able to get more throughput for a smaller size pieces of equipment. Because you aren't blowing a lot of air through the primary chamber, you don't entrain a lot of ash and solid particles out of the primary chamber, so you potentially could have lower uncontrolled emissions than conventional incinerators. Gasification works better in a steam environment, so having the high water content that's produced by processing animal carcasses, it may actually improve the efficiency. The unit that we tested didn't require any pollution control equipment. It ran on natural draft, so there wasn't fans and scrubbers and things like that downstream. So it made it a much more simpler design to send out into the field. Maybe you can do energy recovery. That we never really got to look at that. Potentially, there's lower auxiliary fuel usage than incineration. We weren't able to test that. We had a couple tests that we did out in the field, and some things worked well, some things worked less well, some things we kind of broke the unit and weren't able to fully test them. Next slide. But the general way the gasifier worked is that you would process your feed into small chunks, like about ½ inch size, so it's about the size of the end of your thumb, and it would fall onto the bed, and drag chains would be moving down the bed, so the material would drive off the gases in the primary chamber, and then as it left the primary chamber, it would interact with the flames from a burner, and then go into the secondary chamber, and then make another 180-degree bend backwards and go up the stack after getting dilution air. So there wasn't any fan required for sucking the gases through the system. It was all done through natural draft. Next slide. Now, a key element of this is that you can't take a whole animal and put it into a combustor and get very good performance, because you have a mass of dense cold material that has a lot of water in it. So for most of the mass mortality type of portable incinerators, you're going to have to be looking at some kind of feed size reduction concept. This is what we had for the gasifier. There's variants on this that would work, but in general, you would do some kind of initial size reduction. We had a pre-breaker, and then moved it to a different process, which was a finer, and in order to get it down to the small size, then it went into an accumulation bin and got augured into the gasifier. So whatever type of transportable technology you have, you might need some kind of size reduction technology like this. If you go to the next slide, I think we have a couple pictures. This was the pre-breaker and feed system. You can see it has like a big chute at one end. And this is where one of your main vulnerabilities is for emissions of pathogens, is the feed processing, because you're essentially violently agitating the animal carcasses that might potentially have viral load or bacterial load in them. And so there's a potential for aerosolization of your pathogen there. If you go to the next slide. There's a picture of the gasifier as it was configured for, we had it out in the parking lot of Valley Proteins down in Rose Hill, North Carolina. They had a rendering plant, and they diverted some of their feed for us to use. Next slide. Now the unit was fed by essentially loading the animal carcasses into a bobcat and dumping them into the feed chute. And you could see when you did this, you could see a cloud of aerosol being produced by this. So in actual practice, this would probably be one of the main ways that pathogens get released from these transportable technologies, and it's kind of secondarily related to the technology itself, and more related to the feed processing part of it. Next slide. Here's a picture of the material inside the gasifier. You can see it's obviously at a temperature well above where any potential pathogens could be surviving. We even did amino acid tests on ash as a surrogate for prions, and it was non-detects for amino acids in this material. Next slide. So based on my experience and what we've seen in the field and what we've seen in our pilot scale tests, is the emissions from pathogens from these type of systems in the stack and the ash is highly unlikely. Probably your processing of your feed materials is where the potential for pathogen release is. Also from runoff from the liquids due to the decomposition of the animals as they're staged for processing. The aerosolization due to the size reduction equipment, those seem to be the potential main sources of the pathogens escaping. As far as countermeasures for this, one of the things we talked about but we never tested was to install it like a shroud around the size reduction equipment that would run at negative pressure, and then have the shroud vented into the high temperature part of the system, so that any pathogens or aerosols that get generated due to the mechanical size reduction get sucked into the high temperature freeboard of the incinerator, and they undergo the same residence time that any of the pathogens would get that were driven off the burning carcasses. And obviously, catching the runoff of the liquids would be very important there. Next slide. The other technology that we've been looking at is air curtain burners. They're commonly used for storm debris. They were used for animal carcasses in the last HPAI incident in the Midwest, I guess two years ago. They're used a lot when there's like a hurricane and they have a bunch of animal carcasses resulting from the storm. They're like an open top dumpster, and they have an onboard generator with a big fan, and it injects air into the open top box at a downward slope. So you end up getting a recirculation zone, and your residence time of your gases in the high temperature zone is much longer than would be calculated just based on the flow rate and the size of the box. They typically don't have a lot of emissions measurement requirements. I believe for the Clean Air Act, I think only mandates opacity. I think states can mandate more stringent than that, but these things are not really amenable to doing stack testing on in such a way to figure out what the emissions are. So a lot of them just do opacity. Next slide. So one of the things we wanted to look at was if you're using one of these units to process animal carcasses, we wanted to see at what point, as you increase the feed rate of the animal carcasses, do we start seeing pathogens breaking out of the system. And we couldn't do this on a full-scale unit because you need about 100 tons of trees a day and a lot of dead animals. So we built one that's about the size of one of those dorm room fridges. And we had a company do fluid mechanics modeling in order so that we could achieve a similar fluid mechanics as the full-scale units as we could within the constraints. And based on our shakedown testing, it does mimic the emissions of the full-scale ones relatively well. We're within, a factor of 2 or 3 of what you see from the full-scale unit. So we think it's a pretty good simulation. Next slide. So the question we wanted to ask is, if you're monitoring these air curtain burners for opacity, for example, and you start feeding it or operating it in such a way that the emissions start deteriorating, is that a conservative measure of whether or not you're going to start seeing pathogen destruction, or pathogen destruction deteriorate? And so if you go to the next slide, there's kind of a graphical illustration of this. What we want to do is increase the feed rate of the animal carcasses at a constant feed rate of the biomass. And once we hit the point where the emissions are unacceptably high, and you'll see when I show you the data from this unit, it's obvious at what point that occurs. We wanted to see if we're still achieving effective destruction of the pathogens. Next slide. So again, we fell back on our old workhorse Geobacillus stereothermophilus, and we put it into Cornish game hens, because this is a pretty small unit, so they're a little smaller than chickens. We injected a large quantity of the spores into the body of the birds, fed them into the feed chute by gravity, and we used 2x2s as our biomass feed rate, or our biomass supplemental fuel. We had thermocouples instrumented on various points in the unit, and we did this all inside our burn hut, so we can measure the amount of air that's going through the system, and we can back calculate all of our emissions data to the amount of material that was burned. And then we ran it all through a bag house and a HEPA filter so that we weren't going to be emitting anything out the stack of concern. Even though the surrogate spores we were using are non-pathogenic, we still thought it best to try to capture everything we could. Next slide. So we targeted 25 pounds an hour of wood, and then we were using the whole Cornish game hens, and we fed them at varying intervals. So we fed them constantly, fed them every 2 minutes, every 4 minutes, 6 minutes, 8 minutes, and 10 minutes. And each one was inoculated with 10 to the 6 spores of Stereothermophilus in 10 mils of growth agent, growth media. Next slide. So what we wanted to do is find a scoping test to identify the appropriate baseline conditions, and we ended up settling on the baseline conditions, which are consistent with what was in the Kansas State carcass disposal report, which is a ratio of wood to birds of 2 to 1 on a mass basis, and it ends up being 1 bird every 10 minutes was our baseline. And then we gradually started feeding in more birds in a shorter amount of time until we started seeing things really go to hell, for lack of a better term. And then we backed off from that and did sampling. So there were 2 conditions we did a lot of sampling at. One was at the baseline condition, and one was at just prior to where the emissions really started going down. Next slide. So we measured the temperatures in the firebox. When it was all done, at the end of the day, we let it cool down, and the next morning we grabbed an ash sample and we grabbed the bone fragments from the birds out of the beds, analyzed them. When these air curtain burners are operating, you end up with larger flyaway embers and things that don't even have enough. They're too big to really get entrained into the gas. So they kind of just drop out on the floor near the unit. So we took samples of the floor sweepings, we called it. We did wipe samples of the walls of the burn hut, and then we used, along with various gas analysis equipment, we used SKC biosamplers to get a gas phase spore concentration. SKC biosamplers, they're kind of look like a stack sampling device, but they use an oil-like media in them, and they have a special design of the fluid mechanics in order to make the gas sample impinge onto the oil in such a way that it forces whatever biologicals are in the gas phase, it makes them go into the oil, and then you analyze the oil. Next slide. Okay, so the way we did this is we'd start the gas monitors, wait for them to stabilize, start the wood, wait for it to stabilize, and then we'd start putting the poultry in, and then we would start doing the samples after we started feeding the poultry in. And we'd do after we finished feeding the poultry, we left the wood in for another hour in order to simulate what would happen in a real operational scenario where they may feed your dead animals for a while, but at the end of the day, they want to bring the unit back to baseline operation before they stop feeding for the day. So that's what we tried to simulate. And then we decontaminated the burn hut and the pilot scale air curtain burner at the end the next day after we took our samples. And we used spore cleanse, which is I believe it's a peracetic acid and hydrogen peroxide mix. It's a sporicidal disinfectant. Next slide. So this is an example of our feed rate. There's a couple outliers in the birds, because we're feeding them at best we could at intervals. But you can see this test, we started at a low feed rate and started gradually up to a higher feed rate. If you go to the next slide, this is an example of the carbon monoxide and hydrocarbons. And you can see how when we're just feeding the wood, it's kind of down there below about 200. When we started feeding the birds in, it went up to 300-400. And when we got to the point where we were feeding too many birds, it shot up like another almost order of magnitude and started getting unstable. If you go to the next slide, where we're looking at the temperatures, it's even more obvious that when you get up to about somewhere between 11:30 and 12:30, you can see where the temperatures are wildly oscillating. That was the point at which we decided that the emissions were too far gone, and we backed off from that feed rate a little bit. So whatever the feed rate was at about just before 12:15 or so, that was the feed rate we used for the high poultry feed rate, and the feed rate we used down around 10 in the morning was what we used for the low poultry feed rate. Next slide. So here's an example of the data on the temperatures, and these temperatures are relatively consistent with what you would see in a full-scale air curtain burner based on the testing that we've done and literature values. Next slide. Here's different feed rates of birds. You can see that as you increase the frequency of the poultry, the emissions go up significantly. This was hydrocarbons and carbon monoxide. Next slide. And what we found was that even when we were operating on the ragged edge of making the whole unit flame out and quench, we did not find any viable spores in the air emissions at all. We found some viable spores were detected in the residual poultry bones, 1 out of the 8 tests. In the floor sweepings, we found some viable spores in the floor sweepings. So these were the particles that essentially got lofted into the air from the unit, but they were too large to get entrained into the main gas flow, and they just kind of fell to the ground. and we didn't see any viable spores on any of the post-combustion white samples, and in the residual ash, we didn't see any viable spores. Next slide. We did some positive and negative controls to make sure that we weren't just having artifacts associated with the facility itself. So we did one control where we injected the inoculum directly into the exhaust duct, and we got very good recovery. We did another control where we injected the inoculum directly into the freeboard of the burn hut, and we got very good recovery on that. We also did one where we injected the inoculum directly into the burn hut exhaust duct while the wood was being burned in the air curtain burner. And again, we got very good recovery. So we are fairly confident that we were not destroying the spores while they went from the burn hut into our gas samples, and that we weren't losing them somewhere we thought we weren't losing them. So we're relatively confident that the data that we observed are valid as far as where the spores go and what's left over afterwards. Next slide. So we did not see significant differences in the viable spore results at the test conditions where we had a relatively low feed rate of birds and a relatively high feed rate of birds. So within the limitations of the experiments, it looks like there were not any viable spores released from the combustion of inoculated poultry, even at feed rates that resulted in pollution emissions a factor of 5 higher than the baseline emissions. Next slide. So as far as a bottom line, it looks like the transportable incineration technologies appear well able to control pathogen releases. The environmental monitoring necessary to maintain compliance appears to ensure little to no release of pathogens. The air emissions and the ash don't appear to be significant potential sources of the pathogens, provided the unit is operating correctly. It seems like the auxiliary equipment associated with implementing the transportable technologies is the main potential source of the pathogen releases. So the handling of the animal carcasses, size reduction equipment is a big one for making aerosols, runoff of the liquids, and then decon of the system after use. You have to make sure that as you return it back to sending it on its way to where its next destination is, making sure that there isn't any residual pathogens then. Those appear to be where the main potential source of the releases are. And I think that may be the last slide, other than maybe our disclaimer.
Yeah, it looks like just your disclaimer.
So I'll be happy to try to answer any questions.
Paul, this is Lori Miller. I just wanted to thank you for that presentation. I think that's, I have followed your work over the years at, your work at EPA there, and am always impressed with the quality of the work and the information that's gained. But to see it all put together in sort of a summary of the various projects is really, helpful. It's a different perspective. So I wanted to thank you for that. And, this is great material.
Well, you're welcome. We love working with you guys. I think we're all kind of like voices crying out in the wilderness, trying to find somebody else's money to spend to get some of these important pieces of work done.
Yes, and even more crying, I think, will be in the near future.
Yeah, probably not. Probably right on that.
How about technical questions from the audience, or any other questions?
Hey, Paul, am I coming through Nathan Birnbaum?
Yeah, Nate, you're fine.
Yeah, okay, thank you. I was intrigued about the ceiling tile. what is it composed of, and why is that so resistant to your systems for inactivating the microbes?
It's made out of like an inorganic fiberglass type of material with a little bit of binder in it, and it has a lot of inorganic material in it, like I think maybe like calcium carbonate. I think we analyzed it once, but I can't remember what it actually was. But the stuff is extremely lightweight, and it's very absorbent. It holds, I think, more than twice its weight in water. And so when you combine those two things together, it takes a long time to change the temperature. The heat capacity of the ceiling tile is very high, and when you've soaked it in water, the heat capacity is even higher. And so it took 35 minutes we were making Duraflame log size bundles that we were embedding the spores in, and it took a half hour, 35 minutes before the water boiled off. So ceiling tile is particularly pernicious when it's wet, because it just it's extremely refractory material.
So if you have a spore release in a facility, will, say, chlorine dioxide gas, will that penetrate the ceiling tile to inactivate the spores?
Yes. Yeah, okay. Ceiling tile is one of the things that the fumigants do a relatively good job on, especially chlorine dioxide.
Okay, so, and hopefully you won't need to incinerate. Okay, thank you.
Bleach would also work pretty well too, but then you'll have wet ceiling tile if you spray it with bleach.
Okay, thanks again.
Any other questions for Paul? All right, hearing none.
Well, I got those slides cleared, so Andrew, if people want a copy of them, feel free to send them the PowerPoint.
Okay, great. Thanks so much, Paul. And thank you very much for your time today. It was very fascinating.
Well, I appreciate the opportunity, and if anybody has any questions, you can email me or give me a call offline, and we can talk about it.
Thanks again, Paul.
You're welcome. I guess we'll see y'all later.
Okay.
Thank you so much.
Okay, thanks, Drew. Bye-bye.
Bye.
Bye.